Hi class, in this video I want to do just a quick introductory to sequences. So in Calculus 2, a sequence can be thought of as a list of numbers written in a definite order, so like A1, A2, A3, A4. What these subscripted numbers are is the number A1 is called the first term, A2 is the second, and the general A sub n is just the nth term, right? So the nth term can be whatever, it's just how we identify it. So we will deal exclusively with infinite sequence. So each term a sub n will have a successors of a n plus 1. So there won't be a finite number of terms in our sequence. It'll go on forever. All right, that's called an infinite sequence. All right, so notice that for every positive integer n, there is a corresponding number a n. And so a sequence can be defined as a function whose domain is the set of positive integers. Like there's no a sub negative 1. It's just the positive integers. All right, but we usually write a sub n instead of the function notation f of n. All right, this is really because they're positive integers. All right, for the value of the function at the number n. So notation. So the sequence with the bracers a1, a2, a3, is also denoted just by the bracers a sub n or a sub n starting at n is equal to 1 and going to infinity. All right, some sequences can be defined by giving a formula for the nth term. All right, so in the following examples, what we're going to do is I'm going to give you three descriptions of a sequence, one by using the preceding notation, another using the defining formula, and a third by writing out the terms of the sequence. All right, and notice that as I do this, that n doesn't have to start at 1. It just doesn't. It can be any integer. All right, so this sequence here, we have the sequence n divided by n plus 1. It starts at 1 and goes to infinity. Another way you could show it is just saying the sequence a sub n is equal to, and then the formula for it. And then here what I'm doing is I'm defining this is the, if you plugged 1 in, you'd get 1 over 2. If you plug 2 in, you'd get 2 over 3, and so on. So this shows the first 4 terms, comma, then whatever the nth term in, and then goes on forever. All right, another one right here using the same. So I've got these bracers here that tell me what the nth term looks like just by itself. The a sub n notation, negative 1 to the n times n plus 1 divided by 3 to the nth power. And here, I'm not going to walk you through it, but this is what if you plug 1 in, if you put 2 in, if you put 3 in, 4, and then so on. Finally here, or another one I have the square root of n minus 3, and here it starts at n is equal to 3. Obviously, you couldn't start at 1 because if you plugged 1 in for n, it would be 1 minus 3. You'd get a negative number under the square root. Not good. So the a sub n notation, just the square root of n minus 3. And I'm just saying here that n has to be greater than or equal to 3. And here are the first 4 terms. If I plug 3 in, obviously I get the square root of 0, and so on. And then the nth term. You can even have trigonometric ones here. So cosine of n pi over 6. And you can walk through and see the same notationary pieces for a sequence here. I actually think this one is the easiest one to work with. It's the least amount of writing, I think, and it's also the cleanest. All right, a sequence such as the one in example 1a, so this one right here we'll work with initially first. This a sub n is n divided by n plus 1. All right, so this a sub n, n divided by n plus 1, can be pictured either by plotting its terms on a number line, like we're shown in figure 1, all right, or by plotting it on a graph, as shown in figure 2. So what this is showing us is just the values of the term. So I prefer this one here, and this is exclusively what we'll actually work with. You know, like when I plug in a sub 7, that's 7 divided by 8. So when n is 7, the value of the function is 7/8. And you can see as we continue to plot the values of the series, you know, kind of what the graph is looking like or moving towards here. All right, so note that since the sequence is a function whose domain is a set of positive integers, its graph consists of isolated points with the following coordinates: 1, a sub 1, 2, a sub 2, so on. You can see them right here, isolated coordinates. All right. From figure 1 or figure 2, it appears that the terms of this sequence, this a sub n is n divided by n plus 1, are approaching 1 as n becomes large. In fact, the difference of 1 minus n divided by n plus 1 is equal to 1 divided by n plus 1. And what that means is it can be made as small as we like by taking n sufficiently large. Right? So this difference here Keeps getting smaller and smaller and smaller and smaller and smaller. That's all we're saying. But it looks like it's converging or moving towards the value 1 here. And if you think about it in calculus, what that kind of hints at is a limit, and that's what we're going to be talking about in a second. All right, so we indicate this by writing the limit as n goes to infinity. Obviously, of n divided by n plus 1 is just 1. So in general, the notation, the limit as n goes to infinity of a sub n equals n, means that the terms of the sequence a sub n approach L as n become large. That's just the general concept of a limit there. All right, so notice that the following definition of limit of a sequence is very similar to the definition of the limit of a function at infinity. All right, so the sequence a sub n has a limit L, and we write as the limit as n goes to infinity of a sub n equals L. Or we can just write it as a sub n goes to L as n goes to infinity. So if we make the terms a sub n as close to L as we like by taking n sufficiently large, so if this limit as n goes to infinity of a sub n exists, we say the sequence converges or is convergent. Otherwise, like if it shoots off to infinity or negative infinity, we say the sequence diverges or it's a divergent sequence. All right, so figure 3 illustrates definition 1 by showing the graphs of two sequences that have limit L. So this sequence goes up above L, but it looks like it's still going towards L from above. This one here, it looks like it's oscillating above and below, but it still looks like it's moving towards L. So the graphs of these two sequences both have the limit as n goes to infinity. It equals this limit or value L. All right, so you will see that the only difference between the limit as n goes to infinity of a sub n equals L and the limit as x goes to infinity of a function, all right, of f of x equals L, is that n is required to be an integer, really the only difference. Thus, we have the following theorem, which is illustrated by figure 6. If the limit as x goes to infinity of f of x is equal to L, and f of n is equal to a to n, where n is any integer, then it's just going to be the same, that the limit as n goes to infinity of a sub n is equal to L. What this theorem basically allows us to say is use all the rules of limits to help us find the limits of series, or all the rules of limits for functions to find the limits of series sequences. All right, so let's work some. In particular, since we know that the limit as x goes to infinity of 1 over x to the r power is equal to 0 when r is greater than 0, we have the following. If the limit as n goes to infinity of 1 divided by n to the r is equal to 0, and that happens if we have r greater than 0. So it's the same as the rule with the limit of the function. So if a sub n becomes large, as n becomes large, we can use this notation. The limit as n goes to infinity of a sub n equals infinity. So if we consider this definition, kind of a flip of it, if the limit as n goes to infinity of a sub n equals infinity, it means that for every positive number m, there is integer n such that if lowercase n is greater than capital N, then what happens is a sub n is greater than m. All right, so what we're really saying here is the sequence, it just keeps, as n increases, the sequence just keeps going up and up and up and up and up and up and up. That's really what this is all saying. So if the limit as n goes to infinity of a sub n is equal to infinity, then this sequence a sub n is divergent, but in a special way. And we say that a sub n diverges to infinity. That's how we define this, or say. All right, so the limit laws also hold for the limits of sequences, and their proofs are similar. So all these similar limit theorems here, I'm not going to go through them all, but I encourage you to have them at the slides as you're going through this lecture. All right, all the same limit theorems hold. All right, and this basically saying if the limits are convergent sequences and C constant, then all of this works. Let's talk about the squeeze theorem real quick. So the squeeze theorem can also be adopted for sequences as following. So the squeeze theorem for sequences, if a sub n is less than or equal to b sub n, which is less than or equal to c sub n, for all n greater than or equal to some n sub 0, and the limits of a sub n is equal, as n goes to infinity, is equal to the limit of c sub n is equal to L, well then also that middle sequence, that b sub n as n goes to infinity, also must equal L. All right, so basically we're saying, the sequence gets squeezed between these two, a sub n and c sub n. All right, another useful fact about limits and sequences is given by the following theorem. if the limit as n goes to infinity of the absolute value of the sequence is equal to 0, this one will be important, then the limit as n goes to infinity of just the general sequence, all right, as n goes to infinity of a sub n is also equal to 0. So the following theorem says that if we apply a continuous function to the terms of a convergent sequence, the result is also convergent. So another theorem, if the limit as n goes to infinity of a sub n equals L, and the function f is continuous at L, then basically what we're saying is the limit as n goes to infinity of f of a sub n is equal to f of L. So basically, if the limit exists, you can plug it right in, is what we're saying for the function. All right, so let's work at another example. For what values of r is a sequence of r to the nth power convergent, so it converges to some value? All right, so we know that the limit as x goes to infinity of a sub x is equal to infinity when a is greater than 1, right? And the limit as x goes to infinity of a sub x is equal to 0 when this a is bounded between 0 and 1. So therefore, putting a is equal to r and using that theorem 3, right, we can have the limit as n goes to infinity of r sub n. Well, obviously, it's just going to shoot to infinity if r is greater than 1. That makes sense. And it's obviously going to shoot to 0 if r is between 0 and 1. So we knew that just by thinking of the function in general, x to the n power. Really, that's what we were thinking, or a to the x power, excuse me, and relating that back to sequences. All right, so it's obvious that then the limit as n goes to infinity of 1 to the n is equal to 1, and the limit as n goes to infinity of 0 to the n is equal to 0. All right, so if on the flip side r is between -1 and 0, then, all right, we're going to look back at this theorem here. Let me go back right here. Then 0 is less than or equal to the absolute value of r is less than or equal to 1. So the limit as n goes to infinity of r to n is equal to the absolute value of it is equal to the limit as n goes to infinity, the absolute value of r to the n power is equal to 0. So therefore, it's the same thing. Even if it's negative, the limit as n goes to infinity of r sub n is equal to 0 by theorem 6. All right, and then obviously, if n is less than or equal to -1, r sub n diverges. So shoot down to negative infinity. So you can see here a visual representation of all of this. If r is equal to 1 or -1, what happens? If r is greater than 1, it's here. If r is between 0 and 1, we can see it shooting down towards 0. If r is between -1 and 0, we can see that it's hovering around 0. And otherwise, it's going to go back and forth between going down to negative infinity and up to infinity. But these graphs also help me see if it converges or diverges. All right, so the results of example 11 are summarized as following. So the sequence r sub n is convergent if you're between -1 and 1 and divergent for all other values. And finally, a sequence a sub n is called increasing if a sub n is less than a sub n plus 1 for all n greater than or equal to 1. That is, as you can see, the sequence is going up. It's called decreasing, all right, if the opposite is true, you can see it going down. And a sequence is called monotonic, all right, if it's neither increasing or decreasing, so it's just staying flat. So a sequence is bounded above if there is a number m such that the entire sequence is less than that number for all values greater than or equal to 1, and it's bounded below if it never crossed a value. And so if it is bounded above and below, then what we say is a sub n is a bounded sequence. So for instance, the sequence a sub n is equal to n is bounded below. A sub n is greater than 0 but not above. So the sequence then a sub n divided by n plus 1 is bounded because 0 is less than or equal, or is less than a sub n is less than 1. So it's bounded between 0 and 1, where this one here is only bounded below. All right, so we know that not every bounded sequence is convergent. For instance, the sequence a sub n is -1 to the n. It's definitely bounded because it's always between -1 and 1, but it's divergent, and not every monotonic sequence is convergent, like a sub n is equal to n. All right, that shoots to infinity. But here's the thing, if a sequence is both bounded and monotonic, then it must be convergent. All right, the fact is proved by theorem 12, but intuitively you can understand why this is true by looking at figure 12 here. So if a sub n is increasing and a sub n is less than m for all n, then the terms are forced to crowd together and approach some limit L, like this. And the proof of theorem 12 is based on the completeness axiom for the set of all real numbers, which says that if S is a non-empty set of non-real numbers that has an upper bound m, then S has at least one upper bound b. This means that b is the upper bound for S, but if m is any other upper bound, then b is less than or equal to m. And the completeness axiom, this is what we're finally pulling towards, is an expression of the fact that there is no gap or hole in the real number line. So we have this final thing that's a monotonic sequence theorem. So every bounded monotonic sequence is convergent.